Page 435, section 7.4. For some reason, I wanted to do derivatives of exponents again, I guess. It says derivatives of exponential functions. It should be logarithmic. 7.4 is logarithmic. All right, so we start off with the formula for the derivative of the natural logarithm. They tell me that the derivative of the natural log of x is 1 over x. And if that were not just a plain x, if we had a quantity here, then we could think of that as u, and so we could say the derivative of ln u, and we would use chain rule for that. That would be 1 over u times the derivative of u. So if you'll notice, if you have 1 over u times the derivative of u, that's going to give you the derivative in the numerator and the original in the denominator. Look at that one more time. If you're taking the derivative of the natural log of a quantity, you're going to get 1 over u, which was the original quantity, times the derivative of that quantity. So another way of writing that would be it's just the original function in the denominator and its derivative in the numerator. And so that's a really cool shortcut that we can use that we'll look at in the first couple of examples. Now, the proof of the derivative of the natural logarithmic function is pretty straightforward. So let's take a second and look at that proof. The derivative of ln x is equal to 1 over x. Here's how we get that. All right, if we have ln x, we talked yesterday about the fact that ln just means log base e, and that we could switch that from its logarithmic form to its exponential form by doing e to the y is equal to x, okay? So all I've done is rewritten ln x as e to the y equals x. So let's go through and take the derivative of both sides. To do that, I'm going to need implicit differentiation, so good review of that topic that we haven't seen for a little while. I'm going to go through and I'm going to take the derivative of both sides in terms of x. So the derivative of e to the y would be e to the y, but y was not in terms of x, so I have to leave a dy dx in there. And then the derivative of x is just 1. So to get dy dx by itself, divide both sides by e to the y. So dy dx is 1 over e to the y. And remember that e to the y was equal to x, so I can replace e to the y with x, because that derivative was supposed to be in terms of x. I can't leave it that way. I need to rewrite it in terms of x. And so we get the derivative is 1 over x. So pretty straightforward for that proof. All right, so look at example 1. Example 1, they tell me that y is equal to ln x cubed plus 1. That's definitely a quantity, so I'm going to have to use chain rule. I'm going to have to do 1 over u times the derivative of u. All right, so if we let x cubed plus 1 be our u, then we would have 1 over u. And then we would need to multiply by the derivative of u. So what's the derivative of x cubed plus 1? 3x squared, right. So 1 times 3x squared would give us 3x squared in the numerator, and then x cubed plus 1 times 1 would give us x cubed plus 1 in the denominator. Let's go back to that shortcut that we mentioned a moment ago. Remember, we said that if you multiply 1 over u times the derivative, you would literally just end up with the derivative in the numerator and the original in the denominator, right? So if I had started this problem and said, okay, I'm going to put my original x cubed plus 1 in the denominator, and I'm going to put its derivative 3x squared in the numerator, I would go straight to my answer. So you can see that shortcut really does work. All right, look at another one. Example 2, we've got the derivative of the natural log of sine x. So let's try that shortcut. What's going to be in the denominator? Sine x. What's going to be in the numerator? Its derivative, cosine x, right. So that would be our derivative. Now we could simplify that a little bit because cosine over sine is cotangent. Yeah, so we could simplify that down. All right, example 3 is a little bit different. This is not the natural log of a quantity, so I can't use that little shortcut of put the original in the bottom and its derivative in the top. This is not the natural log of a quantity. It's the square root of the natural log of x. So I'm going to first need to rewrite this. Ln x square root of that, I could rewrite that as ln x to the 1/2. So to take that derivative, I'm going to need to use chain rule and use our power rule. So anytime that I have a quantity raised to an exponent, remember I'm going to do the derivative of the outside times the derivative of the inside. So if I have any quantity to the 1/2, it really wouldn't matter what was inside those parentheses. When I do derivative of the outside, I'm going to get 1/2, whatever that quantity was, to the negative 1/2. So I don't really care about what's in parentheses, doing the derivative of the outside. So a quantity to the 1/2 is 1/2 that quantity to the negative 1/2. And then, of course, we could put our ln x in our parentheses. All right, then we need to multiply that by the derivative of that quantity. So what's the derivative of ln x? That's the one that we just picked up today. Derivative of ln x, 1 over x, yes. So derivative of the outside times derivative of the inside. About the only way you could simplify that is you could say 1/2 times 1 over x and write it as 1 over 2x. If you'd rather, you could also move that ln x back down to the denominator under a radical since it started that way, but you wouldn't have to. So either way you want to go there. All right, for example number 4, I filled in the first part of that example for you because it gets rather involved. So let's look at that one together. All right, example 4, they asked me to take the derivative of ln x plus 1 over the square root of x minus 2. All right, my problem here is that I have a quotient. And when I have a quotient, I have to do like denominator times derivative numerator minus numerator times derivative denominator all over denominator squared. So it's just going to make a great big mess. So that's why I wanted to write this one out for you so that you could just watch it. All right, remember our formula on the previous page was if you have the derivative of the natural log of a quantity, which we definitely do, that's going to be 1 over the quantity times the derivative of that quantity. So it's like the reciprocal times the derivative, right? So that's the first thing that I need to do here. If this is u, then I have to start off with 1 over u. And as we said, 1 over u is just like the reciprocal of u. So I'm going to take this and write its reciprocal, which would be 1 over u. Now I need to multiply by the derivative. So I'm going to go through and say denominator, square root of x minus 2, times derivative of numerator, so that would be 1, minus numerator, and then I need to work on the derivative of the denominator. All right, x minus 2 to the 1/2. If I take the derivative of that, that's going to be 1/2 x minus 2 to the negative 1/2, and then I need to multiply by the derivative of x minus 2, which would be 1. So again, that's denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. All right, then we need to go through and do some algebraic simplification. All right, so we're going to go through and distribute here, combine like terms, and simplify. All the rest of this is pretty straightforward algebra to lead us to our answer. The reason that we went through that one kind of quickly and that I even wrote that one out for you is that there is a much simpler way to do that problem. And so if I go through the long, tedious way with you and make you write it all out, and then I go, oh, by the way, there's an easy way, you're going to start throwing things at me. So I put that one in there just so that you could appreciate the power of this shortcut. Okay? That's how we would have to do that problem if we didn't have this shortcut. What is causing me problems in that example is the quotient, right? Because I have to do that whole derivative, denominator, numerator. That's what makes it so long and tedious. The same thing would be true if I had a product, right? Because I'd have to do first times derivative of second plus second times derivative of first. It'd be so nice if there was a way to get rid of the product or the quotient. That would change this whole problem, right? Well, this is the natural log of that quantity, right? Remember the properties of logarithms from yesterday that said if you have two things that are being divided, you can break it into two separate logarithms that are being subtracted? And the same thing would be true if this had been a product. If I had the natural log of two things that were being multiplied, I could break that into two separate logarithms that were being added. I just got rid of the product rule or the quotient rule if I do that and made my problem so much simpler. So let's look at this a different way. Instead of working with this as u, let's simplify that logarithm before we even take the derivative. So I could go through and say, since I have the log of two things being divided, I'm going to rewrite that as the natural log of the first one minus the natural log of the second one. I can make it even simpler because I also have a property that says if you have an exponent, you can move it out in front of that logarithm and make it a constant. So I'm going to do that as well, so then I don't even have to worry about taking a quantity to an exponent. So if I'll use those properties of logarithms to simplify this down first, look how much easier the derivative becomes. I can go through and now I have the derivative of ln x plus 1. That's just like the first couple of examples that we were doing, right? Where we could go through and say the derivative of ln x plus 1, if x plus 1 is u, then I'm just going to have 1 over u times the derivative of u. The derivative of x plus 1 is just 1. So remember we said that you could write the derivative in the, the original in the denominator and its derivative in the numerator. All right, same story over here. Bring our constant straight down. And this, of course, is our quantity, x minus 2. So we could go through and say, let's put our original in the denominator, and let's put its derivative in the numerator. And so I'll have 1/2 times 1 over x minus 2, which is just 1 over 2 times x minus 2, and I'm done. That's it. Remarkably easier, right? So anytime I have the natural log of a product or a quotient or a power, I want to take advantage of those logarithm laws from yesterday that will let me simplify that before I have to take the derivative. If I went through and I got a common denominator here, that would be x plus 1 times 2 times x minus 2. If I combine those with a common denominator, I will get the exact same answer that I got up here, but just so much simpler doing it by this method. All right, let's look at example 5. Example number 5 says, find the absolute minimum value of f of x is equal to x squared ln x. So I've got f of x is equal to x squared ln x. I'm looking for the absolute minimum. Been a little while since we saw that idea, right? Remember that an absolute minimum you can find by looking at endpoints or finding your relative minimums. Relative minimums, we have to find the critical numbers first, right? So we're going to find our critical numbers by setting our derivative equal to 0 or figuring out where our derivative does not exist, and then using our first derivative test to test that to see if it's a relative minimum or not. So been a little while since we've done that stuff, so let's go back through that really good review for us. All right, so let's start off by finding our critical numbers. We're going to need to set our derivative equal to 0 and see if there's anywhere that it doesn't exist. So we've got f of x is x squared ln x. If we're going to do the derivative, I don't have like the natural log of a quantity that I could use those logarithm shortcuts to help me. So I genuinely am going to need to do product rule here. So I've got first is x squared and second is ln x. So we can do first times derivative of second. What's derivative of ln x? 1 over x, plus second times derivative of first. What's derivative of x squared? 2x. So simplify that a little bit. One of these x's would cancel right here. So that would leave me with just x plus 2x times ln x. So x plus 2x times ln x is my derivative. That's what I want to set equal to 0 to find critical numbers. All right, notice that I have an x in this first term and I have an x in this second term. So I can take out a common factor of x. So I'll come down here and I'll take out my common factor of x, and that'll leave me with 1 plus 2 ln x. And I'm going to set that equal to 0. So if I set each of my factors equal to 0, I'll get x equals 0, and I'll get 1 plus 2 ln x is equal to 0. Now, x equals 0 isn't possible because remember, when you're working with a logarithm, your domain is x is greater than 0. So if I tried to plug 0 back into this thing, right here, I would get ln 0, which is undefined. So that's not possible. It's not in my domain. So let's work on our other factor then. We had 1 plus 2 ln x equals 0, so we could subtract that 1 from both sides and divide by that 2. So that gave us ln x equals negative 1/2. ln is just log base e. So from what we did yesterday, we could say e to the negative 1/2 is equal to x, and that's going to be our critical number. So I'm going to come over here and make a sign chart because remember, just because it's a critical number does not automatically mean it's a relative maximum or minimum. So I need to check it with the first derivative test. So I'll come over here and I'll plot e to the negative 1/2. I'd really need a decimal for that to know kind of how to plot that. So e to the negative 1/2 is 0.61. So that gives me an idea of where to put it on my number line. So I'm going to pick a test point. I chose positive 1, and I'm going to plug it back into my derivative. Because remember, you're making a sign chart for the derivative. You need to plug that value into the derivative. So I plugged in 1, and I got a positive 1. So right here at 1, it's positive. Cross the single critical number, the sign changes to a negative. So my first derivative test says if the derivative changes from negative to positive at a value, you have a relative minimum there. Remember, for justification for AP, I actually have to state that. I have to state what the first derivative test says so that they know that I know the test. So I would want to state something like the derivative changes from negative to positive at that value. So that made it a relative minimum. And because it was the only minimum that I had, and I don't have endpoints to check, then that has to be my absolute minimum. So that would be my justification. All right, example 6 in the textbook is another really great review problem. Remember, we mentioned the book is starting to give us a lot of really good review for the AP exam. Example 6 says, discuss the curve y is equal to ln 4 minus x squared using the guidelines from section 4.5. That was where we did first derivative test. We got increasing, decreasing, relative maximums and minimums. We did second derivative to get concavity and points of inflection. We found asymptotes. We looked for symmetry. So there were all types of things in that section. And so they go through here and they show you each of those, A, B, C, D, E, F, G, H. They're on page 437. So again, fantastic review problem. We're not going to take 10 minutes to work through that in class, but that would be a great problem for you to look back through as you're studying this section. All right, so example 7. Example number 7 says if f of x is equal to ln absolute value of x, find the derivative of that function. All right, we've learned that anytime we have an absolute value, it is automatically going to be a piecewise defined function. So let's start, before we try to take the derivative of this, let's redefine our function so we know what we're working with. So if what's inside the absolute value is positive, meaning it's greater than 0, we get exactly what we started with. If what's inside the absolute value is negative or less than 0, then we're going to get the opposite of what we started with. So there are two different functions. We've defined our piecewise. So now let's take the derivative of that. So if x is greater than 0, I'm taking the derivative of ln x. So that would be 1 over x when x is greater than 0. If x is less than 0, I'm taking the derivative of ln negative x. So derivative of ln u, remember we get 1 over u times the derivative of u. So that would be 1 over negative x times the derivative of negative x, which is negative 1. So 1 over negative x times negative 1 is going to give us 1 over x. So here's what we just proved. We just proved that the derivative of ln absolute value x is 1 over x no matter what the value is, whether it's positive or negative, because we got the same thing for both parts of our piecewise. So we could say then that the derivative of ln absolute value x is equal to 1 over x. So there's another proof we've proved that derivative formula. Now, if the derivative of ln absolute value x is 1 over x, then it makes sense that if you integrate that answer, you integrate 1 over x, you should go back to ln absolute value x. And you do. And if it's indefinite, as this formula is, then we would have our arbitrary constant plus c. So they give you those two formulas in the textbook on page 438, but we just proved them for ourselves. So let's look at some integration then. Example number 9. We've got the integration of x over x squared plus 1. Cannot integrate a quotient. So we're definitely going to need to use some u substitution. So what do you want to use for u?
X squared plus 1.
All right. I really just have two choices, right? I mean, I could either use x or x squared plus 1. If I use x, its derivative is sitting there, but then that doesn't help me at all with this piece. If I use x squared plus 1, then its derivative is 2x, and its differential is 2x dx, and x dx is sitting there. And remember, I don't have to worry about the constant because I can eliminate it. So if I'll think it through before I start, I probably can save myself having to do a bunch of trial and error. So let's let u be equal to x squared plus 2. And as we said, since its derivative is 2x, then its differential would be 2x dx. I don't have a 2x dx. I have an x dx. So what do? Divide by 2, yes. So du we could say 1/2 du is x dx. So let's replace x dx with 1/2 du, and let's replace x squared plus 1 with u. So what did we say was the integration of 1 over u? We just created that formula a minute ago.
Absolute value.
There we go. ln absolute value of u. That was the one that we just created with the piecewise defined function, right? Okay. So we've got 1/2 out in front. Integration of 1 over u is going to be ln absolute value of u. And then we've got our arbitrary constant. We chose to put the u in, so we do need to back substitute and replace u with x squared plus 1. Now, there is absolutely nothing wrong with this answer. But if you were to look this up in the back of the book, that is not what it would say if that was a homework problem. It would say this. And you'd look at it and go, what's wrong with the book? I mean, the formula says it's supposed to be absolute value. They must have made a mistake. They must have left off their absolute value signs. They didn't leave them off. Why have they replaced absolute value with parentheses?
Because x squared is always going to be positive.
Yeah, there's no way that x squared plus 1 could ever be negative, because x squared is always going to be positive. Add 1 to that, it's still going to be positive. So there's nothing wrong with writing the answer in this way. It's just that this kind of shows a little further knowledge of understanding that you don't need the absolute value. You would not want to skip that step, like on the FRQ on the AP exam. You wouldn't want to skip that and make the reader think that you didn't know there were supposed to be absolute value bars there. But we can simplify that to parentheses instead because of that. All right, look at example 10. Example 10, we've got a definite integral, and we're definitely going to need some u substitution here as well. So, ideas? All right, I heard x and I heard ln x. All right, if we let u be ln x, what's the derivative of ln x? 1 over x, and so the differential would be 1 over x dx. That looks pretty good, right? Your other option might have been to do 1 over x for u. That's x to the negative 1, and so the derivative of that's going to be negative x to the negative 2, and so I probably am, well, not probably, I'm definitely better off going the other route. So again, think through it a little bit, and you can save yourself some trial and error. So we'll have u is ln x, and as you told me, its differential then would be 1 over x dx. So I can replace the 1 over x dx with du, and I can replace this with u. So I just have simply u du. If I'm going to replace the x's with u's in my integrand, then I need to replace the x's in my upper and lower limits of integration with u's as well. So let's go ahead and do that. We can come over here and say, okay, when x was equal to e, I need to figure out what u is going to be equal to. So if x is equal to e, and the formula is u equals ln e, then if I put... or my formula was ln x. If I put e in for x, ln e is going to give me 1. So we can come down here and fill in our 1. Same idea with 0. If we put 1 in for x, we get ln 1, which is 0. So that would give me the integration from 0 to 1 of u. All right, what's the integration of u? What's the integration of x? X squared over 2, right. So what's the integration of u? U squared over 2. There we go. It's a Friday. I gotcha. All right, so 1/2 u squared. We can plug in 1, we can plug in 0, and we'll get 1/2 minus 0, so we'll get 1/2. All right, so here is our homework for tonight on the first half of 7.4, and then we'll finish off the second half of that section next time.